lecture number 4, accuracy, precision, and significant figures. So today we're going to start talking about how we can put significance onto the numbers that we calculate or measure in the chemistry laboratory or classroom. And how we relate those numbers to whether how accurate or precise we are. And we'll define all of those terms in a minute. But first let's start by looking at significant figures. So we're talking about, is the number we get reliable? How certain or sure we are that the numbers that we are using are true? We have some understanding or confidence in those numbers. So we're going to start by looking at rules for governing when we see a number, which of those numbers are significant. And there are excuse me, 5 rules, for determining whether numbers are significant. The first rule is if any digit is a non-zero, it is significant. So like a number 11, for example, that's 2 significant digits. Both of those being non-zero are significant. Number 2, zeros between non-zero digits are significant. So in a number like 101, 101, there are 3 significant digits. The 0 between those 2 non-zero numbers is also significant. Rule number 3, the zeros to the left of the first non-zero number are not significant. So if we talk about 0.1, that first leading 0 is simply a placeholder and not significant. So there is only one significant digit in 0.1. That's the 1. 0.001 again only has one significant digit. All those zeros to the left of that first 0 are not significant. Number 4, if a number is greater than 1, then all zeros to the right of the decimal are significant. So if we have a number greater than 1, if we include zeros to the right of the decimal point, all of those are going to be significant. So like 10.0, that would have 3 significant digits because there's zeros to the right of a non-zero number. And number 5, if a number is less than 1, then only the zeros that are at the end in the middle of the number are significant. So if we go back to the example 4.01, if we point 0.0110, that would have 3 significant digits because all of those come to the right of other significant digits. Okay? So if we're looking at a number, those are the rules that we're going to look at to determine significant digits. We typically don't just look at numbers though, we actually do something with them. So let's talk about how these significant figures carry through some calculations. And we'll see that depending on the type of calculation that we do, the rules that govern those significant digits are different. So let's start by looking at significant figures when we add and subtract. So when we add and subtract, we cannot have more digits to the right of the decimal point than in the original numbers. So for example, if we take 68.34 and subtract 12.583, we see that the 68 number only has 2 numbers to the right of the decimal point, so our answer can only have 2 decimal points at the end. If we carry out the calculation strictly as it's written, we see that we get a number with 3, so therefore we have to round that. So the correct solution to this first problem would be 55.76, because we're rounding up to that first or that last significant digit to get the correct number of total significant digits. And we can do something very similar for this next one. Again, we only have 1 decimal point to the place, so then our answer can only have 1, therefore we have to round the answer to 54.9. Okay? When we talk about, this introduces our first time when we talk about rounding, there's about a bajillion different ways you can round. My personal method, again it's only personal, is that numbers less than 5 I round down, numbers greater than 5 I round up, and then the number at 5 I round to an even number. So that's my rule. You can follow whichever rounding rules you are comfortable with. Now let's talk about significant figures for multiplication and division. The number of significant digits in the final product or quotient is equal to the smallest number of significant figures in the original numbers. So if we take 34.59 times 108.48, right, the first number has 4 significant digits, the second number has 5. We can only have 4 because that's the smallest number, so in our solution we're going to round that to 4 significant digits, which in this case would be 3752. Right? We actually lose decimal places in this case because of the rules of significant figures. And then in the second example we have 5 significant figures on the top, 3 on the bottom, so our answer then must be rounded to 3 places to give us 1.95. Right? Only 3 significant figures. Excuse me. The last thing we're going to talk about is what these significant figures mean in terms of accuracy and precision. We can define accuracy as how close we are to some true or accepted value. So when we're making measurements or we're looking how close we are to the right answer. Right? That's accuracy. Precision, on the other hand, is how close each additional measurement is to each other. Right? So if we look at example A in this diagram, we see that we are both accurate and precise. All the numbers are close to what they should be, that dotted line, and they're all close to each other. So we have high accuracy and precision, which means that we have probably dealing with very small errors. In example B, where all of our numbers are now close together, but they're all far from what we expect them to be, that again, that dashed line, we can say that these are not accurate. We have low accuracy, but we still have high precision. Right? If we look at these values again in this figure B, we see that all of them are above where they're the true value that they're supposed to be. So that introduces a type of error we call systematic, that always leads us to an error in one direction from where we're supposed to be. In this case, always high. Right? So systematic errors are always errors that give us a result or push our results into one direction. If we look at C now, we have the numbers that are sort of around that true value. So, and if we took the average of those values, we would get a value that's very close to the true value. So in this case, in C, we are very accurate, but because the points themselves are very far from each other, we would say we lose precision. Right? Which means there's probably an error associated with these measurements as well. But if we look at those values, some are higher, some are lower. Right? So it appears to be that that error is random. So this is the definition of a random error. It can either be high or low. Right? It just is an error that's associated with the measurement that's sort of random, doesn't really have a detailed explanation. Right? And in the part D, again, now we are above the average of those values isn't giving us the true value. The values themselves are fairly far from each other. So D is our classic example of measurements that are either inaccurate or have low accuracy and low precision. So in class this week we'll be talking about using these significant digits, taking measurements and what that means for significant digits, and also then how the measurements we make can tell us information about our accuracy and precision.
Dad, I done did it.